Today we're jamming mass spectrometers with Bob Marley there. And the latest wig on the mass spectrometers. Actually, before we get to mass spectrometers, I want to do a little bit of review of right-hand rules. Right-hand rules, not left-hand rules. Remember, right-hand rules for positive charge, left-hand rules for negative charge, but 90% of the time we use a right-hand rule. There's two basic types of right-hand rules. The first one's called curly right-hand rules. Curly right-hand rules are ones where something is straight and something is a circle. The first one is when we have a current-carrying wire here, and we have a current going through it. We know that our thumb goes with the current, our fingers curl around in the direction of the magnetic field, and it shows us which way it's circling around. Draw it on there, and remember, it does go in and out as many times as it can, all the way up and down, so we only show one of them, but actually there's lots of them. And then if we take the wire and we curl it around a bar, we can use our fingers to be the current and our thumb to be the magnetic field in the center, and so that they flip. What used to be your fingers is now your thumb, whatever your thumb used to be your fingers. And so the magnetic field goes through the center that way, always points towards north, away from south. It actually also goes around out here, but we just draw it in the center. And we can do that the other way too. If they give us the magnetic field, we can find the currents. And remember, that's called a solenoid or an electromagnet. Since your fingers can be one thing sometimes, and your thumb can be something the other times, the way we remember it is that the thumb is always the straight thing, and you curl your fingers in whatever direction the circular thing goes in the particular problem we're talking about. So here's some problems you can practice on. If you want, you can pause the video here, and then I'm going to go over them. But remember that for this first set, we always go with the current first. The current goes away from plus and towards minus. In this case, it goes down. Finger's going to go in that. Thumb's going to go that way. Our fingers curl around in this direction on this one. That's my magnetic field. And the second one, the current's coming out of the page. So take my thumb out of the page. My fingers curl around in this direction. And this one, it goes away from plus towards minus. Thumb goes that way. His fingers curl over the top. That's my B there. For this next bit, it's the other curly one. I always go away from the plus again, but this time I'm going to go on that, do all my little arrows. This time my fingers going down, my thumb goes this direction, always goes towards north, away from south, away from plus. Draw your little arrows on each one. Fingers go up in this case, thumb goes this way. The positive side of the battery is always the plus, and so it's going to go up at the back. My arrows go down. Really, this is just for you to have done them. Thumb goes that way. Sorry, the video actually is doing them backwards because the way those videos flip around, but that's the way your north-south goes. This last one, I give you the magnetic field, so you're going to draw the magnetic field first. Tip your thumb in the direction of the magnetic field. Your finger's going to curl over the top on this first one. Then you follow them around to show the direction of the current. This is really your answer on that problem. The next one, you do the magnetic field, but it's curled the other way. So even though you take your fingers and you go up, again, this time, because it curls over the back, you get the exact opposite answer. On this one, the magnetic field goes the other way. You take your thumb that way, fingers curl over the top, follow them around, goes that way. So a quick review of all of those. Our other right-hand rule is the flat hand rule, where you keep your hand always flat. And this one, your fingers are always a magnetic field. Remember, you have more than one finger, more than one field. If they're going to go in that direction, your thumb is going to go the way of the velocity up towards the top of the page. And so in this case, your force is going to come out of the page on this problem. This is a plus charge, and so the force is coming out of your palm as if there was a arrow coming out of your palm, so you know which way to do them. On this one, they don't change. Fingers are always a magnetic field, thumb is always a velocity, palm is always the force. So on these, we're finding the force in all of them. If you want to pause for a second here, you can. I'm going to go ahead and do them. On the first one, my fingers come out of the page. My thumb goes up towards the top. Remember, it's backwards because of the video, but if you do that, your palm is going to go in that direction. Make sure you get that answer. In this one, you have to draw the current on, and so the current always goes away from plus towards minus. That's going to be your thumb, and your fingers are going to be the magnetic field. So your palm is going to come out of the page on this one. And so you make the force, circle and a dot, F. On this one, they give you the magnetic field. It's out of the page. Again, current goes that way, and so your thumb goes that way, so out of the page. And so it's going in this direction for the force. The last one, you have to find the magnetic field from this one. So you take this current going down, do your right hand rule, your fingers are going to curl it around this way, which means they come out of the page on this side and into the page on this side. Into the page is the only one you really care about because that's what it's going to be where the other wire is. So you take your fingers in that direction, your thumb goes with the current, which is going to be down towards the bottom of the page, and your force in this case goes towards the other one. So those are your answers for those practice ones. I hit this a little bit in all my classes, but I just wanted to make sure we get this. Because QVB is equal to force, so if you have a particle moving it in a magnetic field, it's going to go in a circle. But if some of that velocity ends up being in the same direction as your magnetic field, that part's going to make it go up, and that's not going to have any acceleration on it. This part's going to make it go in a circle. So if it goes up and in a circle, it's going to make a helical path around and around and around going up. So a charged particle in a magnetic field has three choices. If it's going the same direction as a magnetic field, it'll go at a constant speed. If it's going 90 degrees to the magnetic field, it'll go in a circle. If part of it is each, it goes in a helix. So having described the three ways that a particle that's moving in a magnetic field will move, these are the three ways that AP tries to trick you. So they'll give you this picture and they'll say that it's an electric field instead of a magnetic field. And you have to remember back to a couple chapters ago and not get confused and think that it's a magnetic field. But in an electric field, if you have an electron in an electric field, it always goes opposite the direction of your electric field. So it would go in this direction, that right there, move towards the positively charged thing. The other thing I like to do is I like to give you a charge that's not moving at all. If it's not moving in a magnetic field at all, it's not going to have any force on it at all because only moving charge has a force on it in a magnetic field. The other one is if they put it in the same direction as your magnetic field, remember there is no force on it either. It just keeps moving at a constant speed. Snack time. And remember this week's theme for snack, or this unit's theme, is things that my mom gave me for a snack. Thanks, Mom, for all those snacks. I appreciate you. And my mom loved this snack more than any, and she said it was a perfect snack because it comes with its own container and wrapper. She loved fruit. And the two she liked the most are the banana and the orange because you don't eat that outside wrapper that you've been touching a whole bunch. That's kind of gross. You open it up and you eat the inside. But since Mom, I've learned some things about, like this banana. Like when I ate them from my mom, I would pull it from this side and the top would get all mushy and it wasn't right. And so here's the thing. I read an article about how monkeys eat bananas. Monkeys love bananas. Monkeys don't start from this end, they start from this side up here. I know, amazing. What they do is they take and they pinch that side like that. And then they pull down the sides like this, and this, and this, and this. No mushy part at the top. I'm gonna eat the banana. It was a revelation for me. Great way to open a banana and eat it. Go from the other side. Pinch it. Go. My problem with oranges and opening them was that I love oranges, but I couldn't handle getting all the stuff under my nails and it would get to me. And so I found this really cool way to open an orange. You have to have a knife. That's not so great. But what you do is you cut off the very top of the orange and the very bottom of the orange. Here, I'm going to do that. I got to do it on my thing where you can't see, but cut them off with your knife, like that. And then you take one slice all the way from the top to the bottom of your orange. Go through the thing, and then watch this. This is really cool. You open it up, and all the segments open up into little bite-sized, easily eatable pieces. You just grab the first one off. It's like a little tray of orange peel. It is the best way to peel an orange. Now this is a tangerine. It was small. It was all I had at home. But it works for everything. And they just come off nice, easy little chunks and you eat them. Awesome. It's really one of the best snacks ever. I love it. Okay, so now onto the actual mass spectrometer. Mass spectrometer is made up of two different parts. In the first part, we have crossed E and B fields. By that I mean they're 90 degrees to each other. Our electric field, which is caused by this positive charge and that negative charge there, is going down, the way those little arrows are showing us. And if that's the case, then my force electrical is also going to go down. F, E. Oh, the E doesn't go very well. And then I know that my magnetic field, I can take my fingers, put them into the page, my thumb. My force will then go up magnetic. So go that way, F, B. It's going up. Sorry, those F's didn't work out that well, but you can sort of see where they go. One goes up and one goes down. So as they're going in opposite directions, I know they have to equal each other if something's going to go through. In other words, I have a bunch of velocities going through there, but there are some velocities for which the magnetic field and electric field will be the same. And it turns out there's only one V. If I take QVB equal to QE, the Q's will cancel. And I get the velocity is the electric field divided by the magnetic field. And so essentially this first part is so that I just get one velocity that's going all the way through. Notice it doesn't matter, the mass doesn't matter at all, but the first part of a mass spectrometer is so that I get just one velocity through. And then I take away the electric field, giving me just the magnetic field. And remember from last time that this creates a circle, and we know that QEB equals mv squared over r, so we can find the radius. And now we know the velocity that makes it through, and so from this we can find the mass to charge ratio, and that's something that we get from a mass spectrometer. But this equation here is what we use for the second half of the mass spectrometer, and so essentially we use this equation, and the one that velocity is E over B. Wow, that's not going very well. B. For the two different parts, and that's how we do mass spectrometer problems. So here's an actual little schematic of a mass spectrometer. Notice we have our source here. This is the part where we cross the E and B fields, and we put in a magnetic field, and they curve. And we have different ion detectors there. Those tell us the charge, and so then we can find the mass of the different molecules from the amount that they are bent by the magnetic field. So we learn a whole bunch about really small particles by having detectors there to see what happens to them at the end. Quick list of some things that we use mass spectroscopy for. We can identify things in molecular biology. We can look for toxins because that we know the mass of those, and so we can see quickly whether they're in there or not. And pesticides, same thing. And for really small particles, we can figure out the size based on the mass. Quick notation thing. There is a problem on your quest this time where you need to know the unit vectors. Unit vectors are just vectors that have a little hat over them. I hat, J hat, K hat are vectors that have a magnitude of 1. And they're in the directions of the X, the Y, or the Z plane. And we use those to quickly note different vectors. This is a problem, so you know which one it is. And they talk about it here, and they actually tell you what it is right there, but just have given you a warning ahead of time. And then they'll tell you that the force is so much times, I think in this case, negative J. I don't remember actually, so you have to get the problem. But that's the one to watch for. And more brighter banana. And that's some serious hair. Mine just doesn't really compare, honestly. This song here is one of my favorite Bob Marley songs, and it is also the song that my cousin sang when he was on The Voice last year. Great song. Cousin did a good job. Made on television. Go man, go. Go Bob, go. Really good song. Have a good weekend.